Hello, everyone. I want to talk about the spot speed study, which is your next lab assignment. And here I'm going to give you some context of the lab assignment. There is details on your Canvas page that you can refer to. Um, and we'll talk a little bit about why do we want to conduct the study and what are some of the other ways of actually getting this data. And then we'll talk about what you're going to do for the lab. Okay. And I want to acknowledge Dr. Amir Molan, who helped me prepare these slides. And a bunch of this was his creation based on the lab assignment that we had created earlier. So speed studies. Why do we want to study the speed at which the drivers are driving on the roadways? So there are a couple of things I want to share with you. First of all is this LA Times article, which sort of gets at the heart of the matter. And the link is here. And then this is what the article says. As Los Angeles struggles to reduce traffic deaths, speed limits keep going up. And for the longest time, the law in California and in multiple states actually has been that you cannot have a speed limit. You cannot have a speed limit. You cannot have speed traps on the road. And what we mean by speed traps is that you cannot have a condition on the road that invites drivers to drive pretty fast, but then you set your speed limit too low compared to the speed at which the drivers are driving. So if the drivers choose to drive faster than what the speed limit is set at, then it's not the drivers who are always at fault. It's the speed limit that might be too low. That has been the law for the longest time. Now, the speed limit must be reviewed every 5 to 7 years to reflect the natural flow of traffic. That's what the headline says. You can watch this YouTube video if you would choose, that sort of explains that issue in general. I'm not as opposed to sort of using the 85th percentile existing speed at which the 85% of drivers drive at or below that speed, sort of as a benchmark for your speed limit, as this article is. But I think it's still critical to note that having this data, this posted speed limit reviewed every 5 to 7 years, what type of data they use to do this review is what you are going to collect in this lab. Okay, so that's one important point, is that the data that you're trying to analyze here is very critical in setting the speed limit. That's not the only data we use to set the speed limit, as you will see. And this data, the other types of data have become even more important with the recent passage of the AB 43 that became law in 2022. That basically allows communities to reduce speed limit to protect the VRUs, which stands for vulnerable road users, which are your bicyclists, which are your pedestrians on the road. So if you're seeing fatalities for those road users, communities and the state DOT can set that speed limit lower on streets where you expect those types of road users. So the law is now giving more flexibility for the communities to reduce the speed limit beyond what the prevailing speeds are, at a lower level than the prevailing speeds, which I think is a welcome development. But we should be cautious about this, because just because you set the speed limit to be lower, that does not always mean that the drivers are going to be driving at that speed. If you leave this roadway to be 12 feet wide, even on a city street, if you do not have any speed bumps on the road that encourage drivers to slow down, if you don't put in those types of design measures in place that try to slow down the drivers may still choose to drive at a higher speed, even when your posted speed limit is lower, right? So that is why I still think that we should still be looking at this data, speed data, to make sure that our design is basically forcing the drivers to slow down and not just the speed limit. So when we set the speed limits to be lower, we should probably change our design for the drivers to naturally drive at a slower speed so that we can achieve some safe outcomes, rather than just trying to do that through lower speed limit, because that also requires enforcement. And enforcement, by the way, speed enforcement and any type of traffic enforcement comes with the own issues as well, right? So if you are creating an environment where the drivers are driving at a high speed or a higher speed, but your speed limit is set at lower, even though AB 43, as we said, allows it now, there might be some issues related to how do you actually slow the drivers down when they feel they can drive faster. The way to slow them down is through enforcement. And because we don't have a lot of sort of political will to do automated traffic speed enforcement, we rely on law enforcement to do that. Now, law enforcement is already sort of, you can think of them as, they're already stretched thin in a lot of ways. But if we are using law enforcement, there is some equity issues as well with that enforcement, right? Who do the police officers choose to stop for a traffic stop is a controversial issue with regards to a lot of equity challenges that go along with that. So traffic engineers, to the extent possible, in my opinion, yes, if there are lower speed limit, the traffic engineers should be able to support those lower speed limits by creating designs that invites drivers to drive at those lower speeds. And this is why it's very important for us to actually do the spot speed study at different roadway locations so that we are making sure that our design is commensurate with the speed limits that we are posting at. Okay? This used to be the state law. You always had to do it every 5 to 7 years and make sure that the speed at which the drivers are driving at is as close to possible as the speed limit. Now the law allows more flexibility, but even with that more flexibility, I think it's very important for us to make sure that the drivers are not overwhelmingly driving faster than the speed limit. So this type of studies remain pretty critical. So let me go back to my slideshow now. So I would encourage you to read this news story, watch the accompanying YouTube video, and then just sort of read about AB 43 that allows the communities to reduce the speed limit to protect the vulnerable road users, VRUs. So we use the spot speed data to determine the appropriate speed limit. That's the engineering method. And again, as I said, this is only one piece of it. We also look at the collision data. We also look at, what is the design looking like. You also might want to do that for traffic signal timing. So if you are trying to coordinate traffic signals that are on the route here in San Luis Obispo, if you are familiar with Marsh Street or Higuera Street in downtown, there are multiple signals on that route, and all of those signals are synchronized. So if you encounter first signal to be green, you will not have to stop if you drive the appropriate speed. And what that appropriate speed should be, usually spot speed data would be very helpful with that. And also we want to do safety evaluation. Again, if vulnerable road users are at risk due to higher speed, we want to be able to know that. So that's why and then there are other applications, for example, if you want to determine capacity of certain roadways, and according to highway capacity manual, that also depend on what we call the free flow speed. And we'll get to that discussion in a little bit, but the data for that comes from what we call the spot speed study, what we are trying to do in this lab assignment. Can you think of some ways or methods to measure speed? So one method would be to sort of use a stopwatch and measuring the time it takes to travel or a specified distance. So you basically create a marker on 2 markers on the road. You have a stopwatch. You just basically randomly sample vehicles that are passing from one location to the other and just take the difference. The distance would be known already. So for example, if this distance was like 500 feet or whatever, so you can take the 500 feet and then you look at the time difference of the same vehicle passing point 1 and point 2, and then you do the difference between the time. So distance divided by the time will give you the speed measure. In some ways, that could be a pretty good measure, and I'll get to that in a little bit when we look at the next slide. So that's another way, and this is sort of how your data that you're going to be analyzing for this lab was collected. And then, and we tend, if we had access to radar guns, this is the kind of things that you will be doing. So you basically, it's a pretty easy measure, and I posted a video by Dr. Amir Molan who shows you how to do this in the field. How do you actually point the radar gun and get the speed data? And it's a pretty straightforward process. You turn on the radar gun, and then you point it to an oncoming vehicle or a vehicle that just passed you. And then you look at, and then you press the trigger on the radar gun, and then you get the speed limit reading over here. In this case, it's 32 miles an hour. And but do you see a problem with this type of data collection? I certainly do. I'll give you a moment to kind of think about the problem here. If you would like to pause the video, that will certainly be appropriate to think about the issues that you might be thinking about as you observe these people collecting the data. Now, the problem with this way of collecting the data is that the driver of the vehicle could easily spot these people collecting the data. Now, these people probably don't look like law enforcement, so maybe that won't have that big of an impact. But anytime if I'm driving and I see somebody trying to sort of point something at me and trying to collect the data, I instinctively, for the most part, will slow down, right? So this is a way, this is a situation where what we are observing, they are altering their behavior based on the process of being observed. And that's a big no-no in experimental studies. We never want to have the behavior of something that we are observing altered by just the process of observing. So a better way to actually collect this data would be to find an inconspicuous spot from where the driver is unlikely or less likely to observe you as you collect that data. And that's why sort of like a hidden video camera where you collect the speed data later on might even be a better approach to collecting this data than using the radar gun. But if you do end up using the radar gun, you need to find what we call an inconspicuous spot from which to collect the data. And that could get a little bit tricky, and we'll get into that in a little bit. And why it can get a little tricky, as I said, it's the radar gun. The likely angle that you want to get the data from is less than 15 degrees. So if you are more than 15 degrees away, it introduces, so the best place to get this data actually is right in the front of the oncoming vehicle, right? Which is kind of a tricky situation to be in the middle of the road. We never advise you to do that, right? So, and when we go out into the field and observe the data, I'm sorry. Yeah. So, my apologies, the video just quit on me a little bit here. So what I was saying is that the best possible location for you to collect this data to be right in front of the oncoming car. And obviously that's not a safe situation to be in. And here is the other challenge, is that whenever we go out in the field, I would ask you to put those traffic vests on so that you are, pretty visible to the road users and you're safe on the road. And that's basically the way we do things now. And that makes you more conspicuous to the drivers, and that makes the data collection process all the more challenging, right? So that's why and when you're using radar gun, you have to be very careful how you're collecting that data. Ideally, we want a less than 15-degree angle. If you have a laser gun, the same thing. So less than 15-degree angle, make sure that our errors are minimal in nature, and we can still live with that. We'll live with those level of errors. There's automated methods, so we can put some traffic counters on it or some sort of on the roadside units that can actually collect the data. And they basically work with the same principles. Is like, they look at the two locations, they create two markers on the road, and then they look at the time difference between the two, when the vehicle passes the 2 points. And these methods obviously are much more accurate in nature. There are some good devices out there nowadays. So you don't always have to rely on the radar gun method of data collection, which is a good thing. And then there are some other possible ways of collecting, newer technologies that are coming online that are becoming much better. But then the analysis part of the data remains the same. So the analysis that you're going to conduct for this lab still remains the same. So regardless of where the original data is coming from, the analysis that you're doing for this lab is exactly the same way that we'll always do it. So for the automated method, sometimes we'll put the tubes here, and then those tubes can, can count the traffic for you, can get some speed data as well for you as the vehicle pass on it. Vehicle general flow reports, and then that can automatically report the 50th percentile speed, 85th percentile speed, average speed, 10 mile per hour pace. We'll talk about all of these, the lowest speed, the highest speed, and all of that. So average daily traffic is pretty low on this road, and that might not be enough samples here. And then they must have collected some data, and then they looked at the AM peak hour speed, during the morning hour, 5 to 6, 7 to 8, and all of that. So sometimes these could be pretty automated way of collecting the data, but there might be some issues with it that I'm going to just talk about in a few minutes. So this is a tricky question, how many samples you need to collect. There is a statistical formula to do that. The sample size is given by K times S whole square divided by epsilon square, where N is the sample size that you need. K is the value corresponding to the level of confidence selected. So if you are looking for 95% confidence interval, that value of K will be 1.96. And if you're only looking at 90% confidence interval, the value would be probably 1.62. And then you will learn about this stuff in your Stat 321, which is a requirement for the civil engineering program. So when you do your statistics class, you learn about what this formula all means. I'm not actually going to go into that. It basically depends on if you need a larger sample size, if you want to have a larger confidence interval, if you want to have S is a standard deviation of the sample. If your standard deviation is large, then you're going to need a larger sample. And then if you have a smaller acceptable error, then you're going to need a larger sample. And I hope that all makes sense. If you have a lot of variation in your data and your acceptable error is very, very small, then you're going to need a very large sample size, right? One thing to note about the sample size is that you cannot, like when you're in the field, you cannot just take the data on any car that is passing by. You have to be aware of a phenomenon that we call platooning. And what is platooning? The platooning phenomenon is pretty interesting in that, traffic often will move into platoons. So you'll have sort of one leader, and then there will be like maybe 5, 6, 7, or 8 cars right behind them. Now, basically only one of those people, the person who's at the front, is choosing their speed. Everybody else is just a follower going that. So if you have, let's say you see 8 cars going in close proximity to one after the other, you really don't have 8 data points on the sample. You really only have 1 data point on the sample, right? To get the next data point, you have to have a larger gap and wait for the next platoon to come by. And next platoon doesn't not necessarily will have 8 vehicles. It might just, for you all, it might only have 1 or 2 vehicles. That's fine. But you have to get this next data point, you have to wait for the platoon to pass by. Each platoon just represents 1 data point, not 7, 8, or 10 vehicles that might be part of that platoon. Why is that? Because that is not an independent sample. So when I say we need a certain sample size, this N value, what I'm looking for there is independent data samples. And by definition, because the leader of that platoon is choosing the speed, everybody else is just following them. There's only 1 data point there, not 8 or 10 or whatever. Typically, we consider 100 to 150 observations based on what we know about how traffic moves on certain streets, certain city streets, and the standard deviation that we have historically observed on those roadways. 100 to 150 data points should be sufficient. I think I've provided you 100 observations for different locations within the city of San Luis Obispo. They're all close to Cal Poly campus in the data that I'm going to provide you. So there are 100 observations there, but you can actually use the formula to figure out how many observations you need. Typically 150 observations, 150 independent observations are sufficient. For each direction of traffic, by the way, you cannot get northbound and southbound data from the same spot speed study, partly because of that angle that you need, less than 15-degree angle. It's very it's almost impossible to get that angle for both directions of traffic if you're collecting data from only one side of the roadway. So where should we collect the speed? One thing that we want when we are collecting this data is to be able to get the driver's freely chosen speed, the speed at which they choose to drive at. And because we want to do that, we want to be far from the signals and the stop sign and the pedestrian crossings or whatever. We want to be far from those locations. Because why? Because if you get too close to those locations, the drivers might still be accelerating from a stop or decelerating towards a stop for a red light or for a stop sign for a pedestrian or whatever. So you might get those types of samples. So you have to pick a segment to collect your data where the drivers have fully accelerated to their chosen speed to be able to get this data. So you want to be far enough from a stop sign or a traffic signal and so forth. And then the other thing is that you don't want to be at a congested, you don't want to be collecting this data when there is traffic congestion. So you want to be collecting this data when the drivers are driving at their freely chosen speed that is free of congestion, free of effect of other drivers. Okay, so that's what we want to do, is far enough away from stop sign. And what is far enough away? That might mean different thing. If it's a 60 miles per hour highway, 55 to 60 miles per hour roadway where you're collecting this data, then you have to be a longer distance away from a signal. If there is a signal, for example, if you're on Highway 1, that goes to Morro Bay from Cal Poly campus, you want to be far enough away from the signal because the drivers will take a longer time to attain that speed of 55 to 60 miles per hour that they would choose to drive at. If you're on a Higuera street, for example, or any kind of city street, then you could be a little bit smaller distance away because the speed limit or desired speed might only be like 25 to 30 miles an hour. And that drivers might be able to attain sooner than that with accelerating at a smaller distance. So that's another thing to keep in mind. So here I introduce a concept of the free flow speed. What does it mean to be free flow speed? Free flow speed is the mean speed collected with driver selection of speed is relatively unaffected by other vehicles. So for example, if you're the only car on the road, you can choose to drive at whatever speed you want, and you might only be affected by the fear of a ticket or whatever, or the design elements of the roadway, but that's about it, right? So you want to be relatively unaffected by other vehicles. So what time should be collected? Typically when the density is close to zero. Traffic density means how many vehicles per mile, as close to zero as possible. But obviously if there is zero density, there is basically practically no cars on the road, and that might be a hard time. That might only happen like midnight or whatever. But you also need to collect 100 to 150 independent samples to be able to collect that at a reasonable time. Realistically, when the vehicles have a larger than 3-second gap, you can consider them to be independent samples. And then at that level, the drivers are able to drive at their freely chosen speed. So anytime headway is like 3 seconds or larger than that between two vehicles, you're okay to collect those two vehicles' data. Okay, so that's when this is said to have achieved about their freeway, their freely chosen speeds, their free flow speeds. And that's really the data that we want to collect when we are conducting spot speed studies. What is the free flow speed that the drivers choose to drive at? This is what the data looks like. You can see that this data is divided into 2 miles per hour bin. So you look at the location, the mile marker, the date, the time, the weather condition. You always note that roadway surface condition. If there are like potholes and stuff like that, that might affect the speed. And then you sort of choose the bins on the road. And I think in this lab, I asked you to bin the data into just 1 mile per hour limit. And that's okay because you have individual speed observations. But then here the data is being binned into 2 miles per hour bins, 30 to 32, 32 to 34. And then there is, data was collected with the radar. And then these are your tally marks. And then based on the tally mark, and then you differentiate between PC, which is the passenger cars, if they're running trucks in the mix, And that's okay. If there are trucks in the mix, you're free to collect their speed data as well, because that's also part of the stream. And if there are other types of vehicles that might be there, like buses or RVs, you can note those. And then there is the total. And you could see that, this is sort of the mode of the observations, bunch of the observations. 62 observations fall within 48 to 50 miles an hour. And the way we collect the data, speed equal to 50 go with 50, and the speed greater than 50 go with 50 to 52 bin, right? So speed equal to 50 will go here. So if you're binning it into 1 miles an hour, 49 miles per hour will go here, and then 50 will go here. But if you're binning it between 48 and 50, so if you observe the speed 49 miles an hour, that will go here. If you observe a speed of 50 miles an hour, that will also go here. But if you observe a speed of 51, that goes into the next bin. 52 also goes into this bin right here. Okay. So you can think about any speed greater than or equal to a certain value goes with that bin. Okay. So equal to goes with the 50 miles an hour. So if you observe a speed exactly at 50, that goes into this bin, not in the 50 to 52 bin. So this bin, so what this stands for, I'm just going to try to draw some things here. So if you kind of look at this here, this bin represents this bin, this 46 to 48 miles per hour bin represents greater than or equal to 48. Okay, greater than or equal to 48 goes to I'm sorry, this should have been less than or equal to 48 miles an hour. Okay, less than or equal to 48 miles an hour. Okay, I'm going to go ahead and clear all drawings. I'm going to start drawing again. My apologies there. So what I wanted to point out was that if you have the data less than or equal to 48, but greater than 46, okay? So greater than 46 and less than or equal to 48 goes into this bin, okay? Goes into which bin? So data that is less than 46 miles per hour, greater than 46 miles per hour, but greater than 48 mph, that goes into the bin that I'm about to highlight for you. That goes into this bin of the data. Okay, so less than or equal to 48, greater than 46, less than or equal to 48 goes into this bin. So you can see the equal to sign goes with this bin here. So that's how we always collect this data. My apologies for the errors there. Okay, so the next slide, this is what the data looks like. And then once you have the data, you can actually collect this is the analysis that you're going to be doing. Mode is the value which occurs most frequently. So here, once you create the histogram using Excel sheet, that's the lab assignment for you. Pace is the 10 miles per hour range at which speed the highest number of observations occur. So you're basically going to do a rolling sum of the 10 miles per hour range of speeds, and you could get the value there. So the pace here is the maximum number of observations are between 43 and 53.5 miles an hour. Median is the value separating the higher half from the lower half. So it's the 50th percentile. And then one very important one for our interest is the 85th percentile speed that we're going to talk about. That is where we want to have the 85th percentile speed. The 85% of the drivers drive at or close to that speed. So that should be very close to our speed limit. And if it's not, then we might have some issues. We might have to introduce some speed humps, some design-related things to slow the drivers down. Or, unfortunately, in some cases, raise the speed limit. So that's something that we have to sort of work on. And so this is your job for the lab. You're going to be making these statistical calculations. Yeah. And here's one thing that I want to talk a little bit about just before we conclude. Just talk a little bit about, you might hear different terms and I want you to be clear about this. The design speed is the selected by roadway designer to design the various geometric design features. Design speed of the roadway is defined as the maximum safe speed as controlled by the geometric features. So for example, if you're designing a curve, you could do some analysis of speed of a curve at which the vehicle will not get thrown off the curve. What is the maximum safe speed? And that becomes sort of your design speed in the analysis. And we use sort of laws of circular motion to determine that value. On a straight segment, that might be based on how fast can you brake if you see an object for which you have to react and stop. You learn all that stuff in CE 421, which is your traffic engineering class. But design speed is the maximum possible safe speed as controlled by the geometric feature. Every roadway design project must have a design speed. So we always have those. Reduction in design speeds are often necessary to account for curves and hills, certain right-of-way restrictions. So sometimes you'll see the reduced speed ahead sign, substantial warning sign on other devices. We have to make sure that the substantial reaction distance, like people are able to react to that sign that might be available. So that's also very critical when you're approaching a curve or something. For urban speeds, we typically have a design speed between 20 to 45 miles an hour, and even 45 miles an hour might be pretty large. Lower speed for local streets and arterial streets in central business district. Near schools, for example, will have lower speed, especially during the school hours. Higher speed for arterials outside of the CBD. And I think that's where sort of the challenges of pedestrian fatalities in the United States rising come from. A lot of arterials have higher speed, but then they have a lot of businesses, and then people will try to walk on those streets. And in my opinion, yes, the speed limit should there be lower as well. And that's why you should consider pedestrian activity to be very critical. In fact, if you want to encourage pedestrian activity, you should create a design that encourages lower speeds for the roadways. On rural highways, like 101, for example, 50 to 70 miles an hour. Freeways, 60 to 70 miles for urban arterials. And then sometimes it goes as low as 55, and then 70 to 80 miles for rural. I don't think California has any 80 miles per hour speed, but you'll find as high as 85 in certain segments on freeways in Texas. But definitely those are more outlier type scenarios. Typically 70 to 80 miles for rural areas is what you will observe. Speed limit is typically set lower than the design speed. Maximum allowed speed for a section of roadway established by law, something that we can enforce, typically posted by a sign, 5 to 10 miles an hour less than 5 to 10 miles per hour less than the design speed. So just make sure that you understand the difference between speed limit and speed and the design speed. So those are sort of a little bit different things. Design speed might be safer, but the speed limit will be posted always a little bit lower than that. Sometimes, there might be lower speed at nighttime, and some jurisdictions will have those. Sometimes we'll have lower speed for trucks. And there are, different arguments for and against having these types of different limitations. We're not going to go into that. But if you're interested in this stuff, as I mentioned, you should probably take the CE 421 class that we offer every year at least once. And if you're interested in transportation and traffic engineering. As I said, 85th percentile speed is very critical for us. Speed limits are often determined based on the 85th percentile speed. So we want to have our speed limit basically follow what our 85th percentile speeds are, right? So that makes enforcement of the upper 15th percentile achievable. So anybody who's going over that, we want to be able to enforce those limits. And then we should be able to get that from the data. So when we create the histogram chart and when we create the S-curve that I showed you a few slides ago right here, we can sort of draw a line at 85th percentile and figure out what the speed at which 85% of the drivers drive at or below that speed. And that sort of sometimes often would correspond to our speed limit. And you should be able to derive that from your data when you create that S-curve that I just showed you. So this is how you're going to determine. So this is sort of your 85th percentile. You draw a line from the x-axis at 85, and then you, wherever that line intersects the curve, so you draw a line at 85th percentile all the way to your curve. Where that line meets the curve, you project that point on the x-axis. In this case, it's 45 miles an hour. That is what your speed limit ought to be on that section. And again, if you expect pedestrian activity, vulnerable road user activity, the law allows you to set it a little bit lower. You will need justification for that. And then you're able to enforce it. But again, as I said at the very beginning of this lecture, if this is your 85th percentile speed and you just arbitrarily set the speed limit to 25 miles an hour, you might be able to enforce it whenever you have enforcement resources available, and you're able to sort of ignore the equity issues that follow from enforcement. But whenever there is no enforcement, you will see that drivers just putting all the pedestrians and the vulnerable road users at risk, because your design actually still encourages, because of your 85th percentile, you could see that your design encourages a higher speed of travel, right? So you always want to, anytime you lower the speed limit, a good practice is to encourage that type of speed of travel for to make sure that you encourage that type of speed of travel for through design as well, like by maybe narrowing the lanes a little bit, by introducing some speed humps and things like that. So just lowering the speed limit all by itself may or may not be effective. You need to have some design measures so that actually you're able to bring down that 85th percentile speed. Yeah. With that, I will conclude my lecture, and make sure that you read the lab description and watch this after you watch this video, read the lab description. If you have any questions, reach out during office hours or set an appointment to meet with me. I'll be happy to answer any questions you might have with regards to the data. And then you could see in your lab description, you'll find the group that you've been assigned and the location for which you'll be analyzing the data. Again, thank you very much for your attention. I'll see you around during office hours if you need to. Thank you.